Hey guys, and welcome back to another video. Today we're gonna talk about the discrete Fourier transform. We're gonna be drawing with circles, exploring complex numbers and their correlation to e to the I pi is -1. And then we're gonna be drawing SVGs using epicycles. And now, let's get started. Okay, so now for those of you who don't know what complex numbers are, here's the real number line that you all should know, from -infinity to +infinity. But there's also the imaginary number line, which is perpendicular to the real number line. The imaginary number line spans the numbers from -infinity I to +infinity I. Therefore, you can describe vectors as a real part plus an imaginary part. In this case, 3 plus 2i, where I is the square root of -1. So it's a solution to an equation that doesn't have a real solution, but it allows for awesome mathematical stuff to work, just like the Fourier transform. So let's check out what I can do. Get it? Good one. Well, let's keep going. So here we have a unit circle, but it's in the complex plane. The complex plane is basically spanned by the imaginary and the real numbers. If we have this unit circle, we can define the point up top as e to the I theta, where theta is the angle between the real number line and our point. Therefore, we can describe the point on the left as e to the I pi, or -1. And this works due to Euler's identity, which basically states that e to the I theta is equal to cosine of theta plus I times sine of theta, which makes sense if you think about it, right? You add the cosine of the angle for the real part, and you add sine of the angle as the imaginary part. So we go to the right and then straight up, and we have a point. Now let's keep on rolling, and let's talk about what the Fourier transform is and how it's computed. So right here you can see the formula for the discrete Fourier transform, which basically takes in sample points x of n, which in our case are complex numbers, and produces some coefficients that we can use to draw epicycles. These coefficients are what the equation produces and are notated in this big X sub k, where k is the number of the epicycle whose coefficients we calculated. Big N basically notates how many samples we've got, and we basically add all x sub n times these e to the power of something for every epicycle k that we're computing. Now, I told you about Euler's identity, and it's important here, as we can just use Euler's identity to transform this formula into the bottom one. This helps us because it's way easier to calculate, as we don't have to calculate e to the power of something, but rather a cosine and a sine of some normal numbers. Now let's talk about how the algorithm is implemented. We take in a vector of points, which are complex numbers in our case, and we produce a vector of Fourier coefficients. First, we need to map our points to the coefficients. We use the enumerate method to keep track of our k. Then we create a sum, and then we loop through all points in order to recreate the sum in the equation. Then we do our multiplication, add to the sum, and create our Fourier coefficients. The frequency is k, the phase is basically the offset from the start and is calculated using the A10, and the amplitude is basically the length of our vector. Now that's enough math for today, so let's create some points, a rectangle. Let's create a series and sort by amplitude. This is done so that the outermost circles are the smallest. You will see why later. Now it all comes down to drawing the epicycles. And here the t is very important. T is basically 2 pi over the amount of samples we got from our SVG, or rectangle in this case. And you will see why this has to be exactly this and can't be calculated otherwise. Now let's run it, and woo! We've got some circles going. Look at that. If you look very closely, you might even be able to see where the rectangle will be. But we'll see that soon anyways. For visualizing this project, I used a framework called Nanu. It is an open source creative coding toolkit for Rust, and it's awesome. Please check it out, guys. After learning more about Nanu, I finally found out about the update method and created a current sample count, which is used to draw all the lines in the picture. Whoa, we can see the rectangle. This is progress. Looks very cool. You can even see the little arrows drawing it. So now let's get a little bit of personality in the whole project. Therefore, I wanted to pass an actual SVG and use this as an input. We use Fourier himself here. I found this awesome repository called svg2pts, which basically takes in an SVG path and produces a list of points with a given distance between them. Sadly, it was only executable and not a library. I needed a library though. Therefore, I decided to fork the whole thing and use it as a library. You can check the fork out at my GitHub. Now let's draw Fourier with 850 sample points. There he is, looking good and sharp. So 850 epicycles seem like they're enough. Let's change it up a bit and do 250. Now we can see some interesting things. Firstly, we have less samples, therefore it looks jagged. And the other thing is that it moves faster. This is related to the fact that t is 2 pi over our samples. Therefore, less samples equals faster animation. So I told you that t is very important. So let's just change it up a little bit, make it a little bit smaller and see the effect of that. As you can see, it's doing absolute gibberish, which if you think about it, really makes sense. As we calculated the discrete Fourier transform for certain points, and by using this specific t, we are accessing the discrete Fourier transform at the given point. But if we change it up a bit, that point is off. Now, to add on to that, I implemented the possibility for the user to change the amount of epicycles to be drawn. As you can see here, there's 1, there's 2, and there are some epicycles being drawn. By moving the mouse from the left to the right, the amount of epicycles change. And as you can see here, with just 4 epicycles, we have a rough estimation of Fourier, which is actually quite close. And as we increase the number by just some small amount, we get a really good approximation. Look at that. Isn't that awesome? And that's it already. Thank you all for watching. I hope you enjoyed the video. Massive thanks to YouTube channels like The Coding Train or 3 Blue 1 Brown, who really made this video possible. Thanks to you for watching. Check out the GitHub repository in the description below. Check my socials. I'll be back for more.